Chapter 7. Big idea here is conservation of energy, this chapter. And then chapter 8, big idea is conservation of momentum. It's a little abstract, the whole concept of energy, but I think even the concept of force is a bit abstract. If you think about it, what do we measure? We measure distances, I guess positions with a ruler or something, or a tape measure. We can also measure time with a stopwatch. But you never really measure force. You're usually measuring, if you have a spring scale, you're actually measuring how much that spring deformed, or the position of a dial, and that infers the force. Or I guess if you have a strain gauge, it hooks up to a voltage, and you're measuring that voltage on the computer. And so again, voltage you can measure, but the force you sort of infer. So force in newtons is a bit of an abstract idea, but it's quite real. Energy is sort of similar. It's a little abstract, but we do sort of believe in it. We think of it as existing, and we can measure it certainly with numbers. And where it comes in useful, I think you can kind of imagine that if you had a plate, for example, and you knew the mass of the plate was 100 grams, and you dropped it on the kitchen floor and it smashed, and then you took a dustpan and gathered up all the pieces and measured the mass of the pieces. If it said 90 grams, well, I think you would automatically keep looking. You would think that, I guess maybe some of these pieces went under the fridge or something like that. And you'd know that there was still some missing, because you intuitively expect that there's going to be conservation of mass. Just because the plate has changed from being a not broken plate to a broken plate, it shouldn't change the number of, the amount of ceramic in it, or the number of molecules or something that are inside that plate. It's conserved. Mass is conserved. I guess if you got 110 grams and you measured it, you'd really look at those pieces and say, what the heck happened? And maybe you'd notice that there's a marble got swept up or something, or a piece of Lego or something, if it was my house. Okay, so conservation of mass, and the equation for it is that the m initial equals m final. So some process happens, and then over some time, and at the end of that time, you think that the total mass is equal at the end is the total mass at the beginning. Similarly, we are going to use the equation E initial is E final today to solve problems in physics. And then when we get to chapter 8, we'll use this lowercase p as momentum and say the P initial is P final. So there's some changes, but it doesn't change some particular quantity which we can write down, and that helps us get cool answers. So what is energy? Energy is a property of an object, like age or height or mass. You can talk about something as having some energy in it. If it's moving, it has a form of energy called kinetic energy, energy due to motion. If it's in a gravitational field, like here on Earth, we say that it has gravitational potential energy. That's a different form of energy. It's also measured in the same units, so we can convert, between kinetic energy and gravitational potential energy, but we say that there are two different forms of energy, and one particular object can have both at the same time. And you just add them up to get total energy. Energy has units, you measure it. We'll just put here, there is an SI unit of energy. Dead white guy with a last name Joule. And I think it's also 1 J is equal to 1, I think it's a kilogram times meters squared per second squared. And the way I try to remember these units is, have you ever heard of the equation E equals mc squared? Well, m is mass, and c is the speed of light in meters per second, so mc squared is m squared over second squared. So that's joule. And energy is relative. So, sorry about that. The kinetic energy of a car, for example, is one thing from relative to the ground where the car is zipping by. The kinetic energy of your car for the passengers is 0 because there's no velocity there. So, and then it was also mentioned this thing about height, mgh. That height is relative to something. So you could say that something has gravitational potential energy relative to the floor or relative to the ceiling. It would be different. So the equations are: kinetic energy is 1/2 mv squared. V is the speed. And so, once again, I think you got the half is dimensionless, mass is kilograms, and V, speed of the object, is meters per second. So you get meters per second squared. So these things that are moving have some kinetic energy. Potential energy is this mgy or mgh. G here is 9.8. I think you've got kilograms, mgy, you've got kilograms in mass times meters per second squared for g, and you've got meters for the height. So again, you get kilograms meters squared per second squared. So these you may have heard of. What we're going to start with, and I think one of the most sort of basic ways of understanding energy, relating it back to forces, is with work. So work involves force and some displacement or distance. So you get force times distance. We should also do the unit check on that. Force is newtons times distance in meters. A newton, I don't know if you remember from F equals ma, is kilograms times meters per second squared times meters. So again, it's kilograms times meters squared per second squared. So the units check out. There's an equation for work W in your textbook. It's FD cos theta. I'll tell you in a minute where that comes from and what theta is. Theta is the angle between the force that you're applying and the displacement, so what direction and how far the object moves. So two things are occurring when work is done. Application of force and the movement of something by that force. And there's that unit. So the cartoon I've got there of a guy pressing on the wall, he may be sweating and he may be applying a lot of force, but we would say in physics, he's not doing any work on the wall. So when you do work on something, you are transferring some of your energy into that thing. And so you can push on a wall. If it doesn't move, it might be hard to do that, and it might cause you to, flex your muscles or get heated up or something like that. But since you're not transferring energy to the wall in any way, because it is moving, you're not doing work on the wall, is what we would say. Quick little slide here, which is a bit mathematical, but in this course, we will talk about multiplying vectors times each other. And it turns out there's two ways of multiplying two vectors. If you have vector A and vector B, you can do what's called the dot product or the cross product. So we're not going to do cross product today. We do cross products a little later, again in chapter 9, I think, when we talk about torque. Chapter 10 especially, that's cross product. This is a scalar product. So you have two, or also known as a dot product. Fun fact, work is the dot product of the force dot with the displacement. And that's where that cos theta comes from. And the concept is that, you can do it with components ax bx plus ay by. That's a nice little trick. We will use that top equation, the magnitude of A times the magnitude of B times cos theta, where theta is the angle between them. The concept is that if you take A here and look at the component of A that is in the direction of B, and then multiply this times the magnitude of B, that's the dot product. So it's end up being its maximum when the two vectors are parallel, and that's when theta is 0. Its minimum actually goes to its most negative value when the two vectors are anti-parallel. And if you have them perpendicular, then there is no component and you get a dot product of 0 for two perpendicular vectors. Which I think makes sense because, this should be theta here. If theta is 90 degrees, the cosine of 90 is 0. So you get 0 for perpendicular vectors. So we'll do 3 examples of work being either positive or negative or 0. So if you have your hand and you're pulling a briefcase along and it moves, you pull it to the right and it moves to the right, which is where you would expect, I guess, then the force and the distance are in the same direction. You're helping the motion with the force, so I would say that the work is positive. And the way it looks with the equation, I'll just write this down here, you have, remember, W is equal to FD cos theta. Theta equals 0, and so cosine of 0 degrees is equal to 1. And so you get W equals plus FD. It's positive. So I think of that as kind of giving energy to the system. It could be, maybe you're speeding it up. There also could be a situation you're just carrying an object at a constant velocity to the right. So you're pulling upwards on it to prevent it from falling, but the only reason it's moving to the right is because it has some initial velocity to the right. You're not speeding up or slowing it down. Your force here is not changing the energy of the object, so you're not doing work. And the way the equation looks is FD cos theta. This is the force vector. This is the displacement vector. So theta here equals 90 degrees. And the cosine of 90 degrees, and you should check this on your calculator, is equal to 0. So you get W equals 0. And then this is the hardest one to picture, is that your hand pulls the briefcase to the left, but for some reason the briefcase moves to the right. So it is possible for this to happen. It means that it's slowing down. The acceleration from your force, I guess, is opposite the velocity. So it might have some initial velocity to the right, which gives it that displacement. And so the force that you're applying here with your hand on the briefcase is reducing the energy. So we say that we are doing negative work on the briefcase. Hand does negative work on briefcase, so you're kind of sucking the energy out of it. And the way it looks is, remember there was W equals F d cos theta. Theta, remember, is the angle between the displacement and the force vector. So if the displacement and the force are in opposite directions, then I would say that this theta is equal to 180 degrees. It's a whole U-turn kind of thing. And again, you can check this on your calculator, but if you do the cosine of 180 degrees, I think it's negative 1. So you get W is equal to negative FD. So this is kind of interesting because work is a scalar, but it can be both positive or negative. So some scalars like mass is always positive, but work, it's a scalar, but it can be positive or negative, depending on whether you're putting energy into the system or taking energy out of the system. So this is gravitational potential energy, and the nice concept here, so what I tend to think of is if I have like a coffee cup or something, maybe this coffee cup right here, and I put it high up somewhere, maybe I put it right here, and it's full of coffee. To me, that, as a parent, maybe, I just look at that and I'm like, ugh, it makes me feel nervous. And I'm just going to grab it, especially when it's over all these laptops. Lots of bad things can happen. Lots of exciting, energetic things can happen when you've got something with mass balanced at a high height. And that is called gravitational potential energy. It wouldn't be as bad if it's on the floor, because it just doesn't have as far to go. If we nudge it or something, it might fall over and spill, but if we nudge it here, it will pick up a bunch of kinetic energy as it falls and then splash all over the place and cause a lot more damage. But what's interesting about gravitational potential energy is that it's an energy of position. If we take this book and we do some work on it along this path and drop it here, or we take this book and slide it along, do the work of pushing it exactly straight up and then slide it sideways, it turns out that as you do this dot product, you get the exact same answer for both paths. So we're not going to do these integrals, but as you integrate the work done against gravity, it's path independent because gravity is a conservative force. So what it means is that it depends on the initial position and the final position, but not the path in between. So you can write down an equation for it, and that's from your book. The change in PE, or gravitational potential energy, is m times g times h. So it increases with height. And the fact that it increases linearly with height reflects the fact that here on the surface of Earth, gravity is a constant. This G 9.8 is constant with height, approximately. So a domino is a rectangular solid which can be balanced on its edge, and it has some gravitational potential energy, which is maximum when it's standing on its edge. But it's a state of unstable equilibrium, kind of like this cup. So any small perturbation can cause the domino to fall, and then as it falls, it transforms its gravitational potential energy into kinetic. And as it's falling, it can perturb its neighbor, and it turns out that a domino can knock over another domino that's 1.5 times bigger than the first domino. And so you can make this chain of increasingly bigger sized dominoes, which we have. So while John sets up those dominoes, the tiniest little dominoes, as you can see there, I think the smallest one is 1 centimeter high, I'm going to tip up the biggest domino we have, which is over 1 meter high, and it's about 100 pounds. So it's push it. So what I'm doing is I'm going to do work on this domino. I'm going to push it up some displacement and give it a bunch of energy, which is stored as gravitational potential energy. So it had less gravitational potential energy when it's on the floor. I do work on it. Now it's got a higher center of mass. So the center of mass has gone up this distance h. And so that's your extra energy. And all of these have been tilted up to have their own gravitational potential energy. Boom. Well done. So that's an amplification of energy. John put in a tiny, tiny little bit of energy, and then you got this huge amount of energy out. But he didn't really get that energy. It was already put in there by us stacking it up. And since this is a geometric progression, it turns out this was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dominoes. If you had 30 dominoes, the last domino would be like the size of the Empire State Building, and it would still fall over. So. And don't forget, the zero of potential energy can be placed anywhere you want. So here are two people talking about the same rock. Amber's coordinate system is quite sensible. It has 0 at the floor. And so she would see h for the rock to be +1. And so it's a 1 kilogram rock. So it's got mass is 1 times 9.8 times 1 meter. She says, this rock has 9.8 joules of potential energy. Whereas Bill has an equally valid frame of reference in which the ground is at -1 meters, which is fine. He's put his 0 point at the position of the rock. And so Bill says, the rock has 0 joules of gravitational potential energy, and they're both right. What will happen is that if you change the position of the rock, it'll go negative as it falls in Bill's coordinate system, and so that drop in potential energy will convert to kinetic. Whereas for Amber, it'll go just from 1 down to 0, but it's the same change. So this is a whole other way of looking at free fall, is that we have some object. We have been thinking of it as, oh, well, it accelerates as it goes down with 9.8 meters per second squared. Well, here's another way of looking at it. Here, at the beginning, it has energy of gravitational potential energy, but 0 kinetic. And then just before it hits the floor, it has the same energy, the same sum, but the potential energy has decreased, and so the kinetic energy has increased. And since the sum of PE plus KE is constant, it's conserved, conservation of energy, that's why it speeds up. So this is the most important equation, I think, in chapter 7. It comes up again and again and again. I don't know why, but I don't see students write it down a lot, but it's really important. So E initial has a bunch of components to it, maybe kinetic, maybe it's potential. E final also has, parts to it, partly kinetic, partly final, but the sums don't change. Why is thermal energy a type of energy usually referred to as a non-conservative force? I've seen energy lost due to friction always being referred to as thermal energy. I know friction generates heat, but it also generates sound, as well as slightly damaging the surfaces in question. With the energy to make sound and energy cause scratches on a surface also count as energy lost. I might be a little disappointed if the answer is just those losses are negligible. So I think this is a great question. I thought I'd read it out, but this is exactly right. So I think that there's also, like, for example, maybe you have a collision where, even this one, if I drop this and it falls, it doesn't bounce up to the same height, so energy is lost in this collision with the floor for a number of reasons. And one of them is the deformation of this spongy surface. Or you can have deformation of metal if a car collides with a lamppost or something. And a lot of energy does get stored in these deformations. Chemical bonds get broken and things. You have damage. And there could be sound, okay, or something. That sound energy goes out into the world. That might be a little less, but the point is not that these losses are negligible, it's more that they're kind of complicated and that they're lost. So I'll try to use the idea of internal energy or something, but the point is you're not getting that energy back. And I also do feel that even sound eventually gets absorbed in the walls, it turns into heat. This sponginess is probably generating heat as well, so heat is a lot of it. And then there was this roller coaster thing. It was questioned, as a roller coaster arrives at the end of a ride with a kinetic energy of 3 million joules. So maybe it's been zooming around and you're getting towards the end. What happens? Well, it slows down and stops. so that the people can get off without having to jump off. How much work was done on the roller coaster by non-conservative forces while it was stopping? So it's doing negative 3 million joules worth of work. The brakes come on or something. I hold a ball at a distance of 5 meters above the ground and release it from rest. How fast is it going just before it hits the ground? So I could use kinematics and chapter 2 stuff to do this problem, but I'm not going to. Let's use chapter 7 material, energy concepts. It's not necessarily easier, but the point is you can do it this way. So what I would say, I'm also going to draw a diagram, but this is like the initial position. And this is V initial is 0 or something. And then something happens, it falls down, and just before it hits the ground, this is like the final. So it's going some V final. And so what we can say is that this H0 is 5 meters, and this H final is 0. So what we do is we say that E initial is E final. So that's our big equation of chapter 7. Seems a little simple, but what you do is then you expand it out into all the different forms of energy you can think of and just add them up. And so what I could think of is that there's going to be kinetic energy plus potential energy. So, and then there's equations for all these, so it's 1/2 m times V0 squared plus mgh0 equals 1/2 mv final squared plus mgh final. And now some of these are going to be equal to 0. So like the V initial is 0, H final is 0. 0 plus mgh initial equals 1/2 mv final squared plus 0. So that's how I got to this. So I'm writing all these steps down because you don't want to really skip these steps unless you're used to doing them. Figuring out what's 0, what's not, okay? And the conservation of energy concept is that whatever energy, total energy you have at the beginning equals total energy at the end. But some of them are 0. You get V final, which is what you're trying to look for, squared equals GH0, V final. I would say plus or minus, but since it's a speed, I'm just going to use plus 2GH initial. Square root of 2 times 9.8 times 5. And you get 9.9 meters per second. And hopefully this is the same answer you would have gotten if you had used kinematics equations, knowing that the acceleration is 9.8. Roller coaster of mass m starts for a height h above the ground as shown. It completes the loop-de-loop, going whoop around in the vertical circular path as shown. The cart is on wheels on the track, so there's only a regular normal force which pushes the wheels, but does not pull. So I think a real roller coaster at Canada's Wonderland has these safety wheels, which kind of connect on the opposite side as well. So what if there's no safeties? There's got to be some minimum speed before your whole thing is going to fall, like a car on a road or something. Okay, what is the minimum initial height, h, needed so the cart remains in contact with the track the full way around the circle? You may neglect friction and air resistance because they're complicated, basically. Also, if it's a ball rolling, we're going to neglect any spinning energy that it has as it's going. So that's another problem. But not that these things are necessarily negligible, but they're certainly a bit complicated, and it's more fun to just neglect them for now. See if we can express an answer in terms of m, g, and r. I've got here is h, v initial equals 0. And then there's some point right here it has to get to. And this is like a circle, so I think that this distance here, h final, is 2 times r. R is the radius of vertical circular loop. And what we can do is E initial equals E final, and we can say, so I think it starts with 0, and we're trying to kind of think about this final speed here. We've got 0. Plus mgh is what we're looking for, equals 1/2 mv final squared, plus mg times 2r would be that final height. And the m's all cancel out, and you get the gh is equal to v final squared over 2 plus 2 times g times r. So that's sort of interesting. The other thing that I can do is let's consider the free body diagram at this critical moment of the car at the top of the loop. And I'll say that the minimum speed is when the normal force...
It is 0?
0. Yeah, I think that's right. So that's when the thing just sort of loses contact. So you can imagine with this marble, it's got to keep pushing along the track the whole way to stay on the track. If the normal force goes to 0, then boom, it'll just fall and turn into a projectile. So that's exactly it. Free body diagram looks like this. You've got mg, and that's it. You would have a normal force also down, but without the normal force, equals 0, n equals 0. Then I think that's it. The thing that you got is a centripetal acceleration downwards, okay? So because this r is down, right, towards the center of the circular path. And so I would say that F net, kind of in the r direction, is m times a centripetal, which is going to be mg. So you've got mv squared over, I guess v final squared, over r, is equal to mg. M's cancel, and what you get is v final squared is equal to g times r. So that's kind of lucky. What you can do is just plug that in over here. Rather than take square roots, v final squared was already in that equation. So this equation then becomes g times h equals g times r, capital R, I guess. I don't know why I've gone to lowercase r, but you get it. Over 2 plus 2 times g times r. So I think that now the g's cancel, and you get h is equal to r over 2 plus 2r. So I think it equals 5 over 2 times r. So like 2.5 times r would be that initial height. Yeah, we're going to see if it goes up, if it sticks on the track or not, or if it falls. So about 2.5 times. Let it go. Just stays on it. Okay, so that's great. So if we go a little less than that, same height, we put it on here, it should fall. There you go. Normal force went to 0. It doesn't stick to the track anymore. There's no glue force holding it on. If we do more than that, what happens if we start it right up at the top? Woo! Okay, it becomes a projectile off at the end. So we talked a little bit about Hooke's law before when we were talking about elasticity. But basically, if you stretch a rubber band or bend a ruler or something or bend a solid object, the object tries to push back. And so there's this restoring force. We call it a spring force, K times X. K is called the spring force constant in newtons per meter. And the idea is for any spring or elastic object like that, you have to measure it. And the higher the spring force constant, the more stiff that spring is. Now, there's no plus or minus sign in this equation because you're really just doing the magnitude of this force. The direction is that it's the spring always wants to go back to its equilibrium position. So if you compress the spring, then it's going to try to push, right? If you pull the spring, it's going to try to pull. Try to show the direction of the force here, where the 0 point is defined as the equilibrium position of that spring. Also, it's important to note that Hooke's law is approximate. This x has to be pretty small, the displacement from equilibrium. We know that if we overstretch a slinky, for example, it you can destroy your spring and then it no longer obeys Hooke's law. Okay, we know that. Now there's elastic potential energy. What is the work done when a finger stretches a spring originally at equilibrium? And it's going to turn out kind of nicely is that it depends on the position of the end of the spring, meaning that it is a conservative force. So we will be able to define a potential energy for springs. So we can work out what it is. It's force times distance. Hooke's law is K times X. So you might think you do the distance, X times KX, you get KX squared. That turns out to be wrong. It's close. But keep in mind that the force is 0 when x is 0. And so this kx is kind of like the maximum force at position x. If you are pulling it through the whole distance x, that's your displacement. Force will start at 0 and will end up at kx. So you're going to need to average it. And since it's a linear function of x, you can average it by adding the initial, which was 0, plus the final, which is kx, and divided by 2. That's where the half comes from. 1/2 kx squared. It sort of looks like almost 1/2 mv squared, which was kinetic energy for a moving object, but now this is the elastic potential energy stored in a spring that's been stretched or compressed a distance x. It's always positive, so the minimum potential energy that a spring can have is 0, and it can never have negative potential energy. And the 0 point is just when the spring is at equilibrium, and it's not going to do anything. The work done in a spring is equal to the energy you put in that spring in the form of potential energy. So it kind of looks like this. We define potential energy, 1/2 kx squared. Okay, you could then have that potential energy go into moving an object, for example. So we can do an example. A moving car has 40,000 joules of kinetic energy while moving at a speed of 7 meters per second. So I'm going to draw this initial situation. It's going at some speed, it doesn't say the mass actually. V initial is equal to 7.0 meters per second. And the kinetic energy initial is equal to 40,000 joules. A spring-loaded automobile bumper compresses 0.3 meters when the car hits a wall and stops. So I think I'm going to draw it right here as the wall and have some spring sitting there. But the idea, I think, is that initially the spring is at equilibrium. So I would say that x0 is 0, and then what will happen is it'll be a whole other final situation. The car stops after compressing at 0.3 meters. So it's a bit hard to draw this, but there's the wall. Now you've got this compressed spring with a stopped car in front of it. And V final of the car is equal to 0, but now the spring is compressed some distance. X final is 0.3 meters. Does that look okay? What equation am I going to write down? It's my favorite equation. It's good to write down. Now we're going to write down all the things. So the important things here are not gravity, although we could write it down. The idea is that now we've got kinetic energy initial plus potential energy gravity initial plus potential energy spring or something like that initial equals kinetic energy final plus potential energy gravity final plus potential energy spring final. Okay? A lot of these are 0, so we could cross out the thingies that we think are 0. So first of all, we could say that the height is 0, initial and final. It's not going up or down a hill, so forget about gravitational potential energy. Those are 0. Okay, good. What else is 0? I think it stops at the end, because V final equals 0, right? Also, the spring, I think, was originally uncompressed. So now we got a lot of zeros. Let's try to write this all down. We've got 1/2 the mass of the car. I don't need to do that because I was given the initial kinetic energy. Kinetic energy initial plus 0 equals 0 plus 0 plus 1/2 k times x final squared. And what can we learn about the bumpers? I think what we're going to try to find, let's find the spring constant. That's something we can know about the spring. It's called the spring force constant in our textbook. Ke0 is 1/2 k x final squared. We have all these numbers except k. So there's a 2. K is equal to 2 times kinetic energy initial divided by x final squared. 2 times 40,000 divided by 0.3 squared. K is equal to, I got 8.9 times 10 to the 5 units. Newtons per meter, thank you. Yeah, someone yelled that out. Awesome. I just used SI units. I had joules for the energy, and I had meters for the distance. I was very careful to keep everything in meters, kilograms, seconds, and joules and newtons and stuff. You get newtons per meter. So sometimes you see these energy curves where you've got position and then potential energy. So shown as an energy diagram of a horizontal mass and a horizontal spring. The potential energy is actually a parabola, where this is the equilibrium position, and then you've got 1/2 kx squared. And this potential energy curve is determined by the spring constant. You can't change it, but you can set the total energy is kinetic energy plus the potential energy. So the kinetic energy here is equal to the total energy, which is a constant, divided by this potential energy curve, minus, right? Spring. So it's this difference. This difference is the kinetic energy. So what's interesting is that at this point, the kinetic energy is largest, so it's going fastest at x equilibrium. Then it goes down to 0 at these, this point and this point. This is kinetic energy equals 0. So this is what's called a turning point. When the kinetic energy goes to 0, that's when the velocity goes to 0. So that's when the velocity can go from negative to positive on one side or from positive to negative on the other side. So this, what you've done with this potential energy curve and then the cap, which is the total energy, is you've trapped this particle to be in this position. You see this coming up a lot, for example, in physical chemistry, where you're talking about an electron or two hydrogen atoms in a covalent bond, for example, here. So you've got the two hydrogen atoms, H2 protons, basically. They have some potential energy curve between them, which is a function of their separation, the distance between them. And so they can, if they've got some total energy here or something, then they can bounce around, have some kinetic energy in this region. And so the two protons are confined to be in that region. And they're going to settle down to be at its sort of equilibrium when they get to this minimum configuration. And this is what sets the size of an H2 molecule. And so this has something to do with the electric force. It's an electrostatic force, but it's using these potential energy curves. So this is a spring. So there's two conservative forces in this course. One is the force of gravity. So you pass the same height, you'll go back to the same gravitational potential energy. There's also spring potential energy. So if you compress a spring, then now this spring stores a bunch of kinetic energy. So if you release it, a whole bunch converts to kinetic and jumps all over. It also can store kinetic energy if you stretch it, and then it can spring that way. But there's an equilibrium length where there's 0 potential energy. If you stretch it, you've added potential energy. If you compress it, you've added potential energy. And there's this 1/2 k x squared thing. So I'm going to do this, where I put the ball in, then I compress this, so I push this down. Now I'm adding all this potential energy to the ball. There we go. So now it's loaded. So it has some energy in this configuration. And then there's sort of 3 points of motion. There's the point A, where it's right down here. Point B, where it's maybe at this sort of 0 height. And then point C, where it's way up there and stopped momentarily. So when it's at that 0 height, it's moving quite a bit. So you can look, if you want, at all the different forms of potential and kinetic energy. So and this is kind of the equation that I like to use here. You've got potential energy of the spring. Then there's gravity. G stands for gravity, S stands for spring. So there's 2 potential energies, and just add them. The gravity one can be negative or positive. The spring one, I think, is always positive. It's just squared in there. Then there's kinetic energy. That's a 1/2 mv squared. And W is sometimes called WNC in your book for non-conservative forces. So what it means is that when I was pushing down with this stick, I guess, or if there was any friction on the way up, those would be work done by non-conservative forces, either add energy or take energy away. But those ones, I'm just going to say those are 0 for the motion here. And then there's all the final. So, and you can decide which is initial and which is final. So, for example, you might consider just from A to B. Well, from A to B, the potential energy of the spring at A would be 1/2 k times h min squared, because that's the distance that we've compressed that spring. And then plus, I would say negative at point A, m times g times h min, because it starts off with a negative potential energy, but then plus 0. And then at point B, the potential energy of the spring is 0, plus the potential energy of gravity is 0, and then plus the 1/2 m times v b or something squared. So that's sort of what your conservation of energy looks like. So all that potential energy, well, actually, you've gained some gravitational potential energy. You've gone from negative mgh to 0, actually, but then you've lost a bunch of significantly more potential energy from the spring, so that's going really fast at this point. And then from there, you could go up to the height c. So at point B, again, you've got 0 plus 0 plus 1/2 mvb squared plus 0 work, because we're not considering the non-conservative forces in this case. And then up at this height c, again, the spring stays the same. It's not involved at this point because it's not still connected. It leaves the spring. But now you've got plus m times g times h max. And then it stops. And the other thing you can do is you could choose to skip point B and just go straight from point A all the way up to point C. If you want, then you'd say, oh yeah, so at point A, you've got 1/2 all the positive energy, h min squared, minus mgh min plus 0 equals 0 plus mgh max. So you start at a negative, and you end up at a positive height. And that's maybe the simplest way to calculate the height, is don't even worry about the kinetic energy. You know that it gets converted to kinetic energy in the middle, but it starts at rest, ends up at rest. So friction is one of these non-conservative forces that can do work. So answer is yes, it can. And the idea is that, again, if you're pulling something along a carpet, it might start at rest, end at rest, but as you're doing it, you are doing positive work on the box with this tension, and friction is doing negative work on the box, is the way that I would put it. The effect of friction is a change. You can talk about it as negative work, and the other way that I like to think of it is that, remember when I was rubbing my feet on the floor and there was all this heat left behind? That is somehow increasing the internal energy of the system. So it's sort of two different ways. You can put it as this increase in internal energy and put it on the right-hand side of the equation as positive, or you can say it's negative work and put it on the left-hand side. But this is the way I like to do it, is that this is the work done by the rope, and this is this change in internal energy, it's done by friction. But either way, I think they end up, if it starts and ends at 0. So, and the way I like to think of work is that work is the change in the total energy of the system. So by pulling this, I'm adding energy to the system. So remember, a change in energy is the final minus the initial. So you can rearrange that as initial plus the delta equals the final. And that's what the work is. The work is some change in energy from outside non-conservative forces. So this is what the main structure of the equation is. W is the work done in between the initial and final states. So this looks like E initial equals E final, but then there's some work done by non-conservative forces. I want to talk about power. So in physics, the word power refers to how fast work is done. It's this change in energy divided by the time it takes to change that energy. And there's a SI unit for it. You put joules is the unit of energy or work, and time is measured in seconds. So joules per second was named after James Watt, who developed the steam engine. 1 joule per second is 1 watt. And then a kilowatt, you hear about a lot, is 1,000 watts. So, and this is from your textbook, this example that this woman starts at the bottom of the stairs at rest and then ends up at the top of the stairs running. So what's her change in energy, the work done on her as she goes? Well, it's going to be the final kinetic energy plus the final gravitational potential energy. So it's the mgh plus the 1/2 mv squared. That's your work done, and then the time it took her to do that is t, and if you want to know the power consumed, then you just divide. So I'm going to talk a bit about electric power. So the unit of power is the watt, which is 1 joule per second. If you are paying for your electricity, you look at your bill, it's called Hydro. One is the company that sells electricity in the province. I guess Hydro stands for hydroelectric power because a lot of Ontario's power is generated by waterfalls or dammed up waterfalls, is kilowatt hours. So a kilowatt hour is actually a unit of energy. It's the amount of energy used by a power of 1 kilowatt for 1 hour. And the reason that this is a good unit, if you convert it to joules, is that it's about 3.6 million joules. So it turns out a joule, I guess another way of putting a joule is that it is the amount of work you do if you push with 1 Newton of force over 1 meter. I don't know if you ever remember measuring that 1 Newton with that little tiny little spring scale. They're a very weak little spring scale. A newton's not much. It's just a few grams of force, right? So, and a meter's not that much. So a joule is an extremely tiny unit of energy, and it's not very convenient to use. So when they charge for electricity, they charge it in kilowatt hours. So this was a good question. You would think a kilowatt hour would be a unit of power, but the idea is that kilowatt is a measure of power, hour is a measure of time, and time times power gives you energy. And this is where energy is coming from in Ontario over the last year. We have a lot of nuclear power plants in this province. 35% of the power that's lighting this room right now is coming from nuclear fission. Then you've got gas that's being burned. You've got hydro, which is basically water. When rain comes down, it gets stored at higher elevations. Then as it falls down, you take the energy from that. Wind power, so there's a lot of big turbines around the province, and there are solar farms as well that generate electricity. So this is my garage, actually. I have 12 solar panels on the south-facing roof of my garage that I installed 2019. And this actually shows, so it actually monitors how much energy every month that it produces in kilowatt hours. And so you can see it's a lot less in the winter than it is in the summer, and it also depends on cloud cover and things. The idea is that I don't actually have any batteries. What I have is on the side of my house, I have a bi-directional meter that they had to install. So sometimes I'm over-generating, generating more power than I'm using, and then it just goes back into the grid, and I guess my neighbors use it. And then the rest of the time I'm paying. So they just subtract how much I generate off my bill every month, compute it. So a 1 megawatt hour is 1,000 kilowatt hours. So the cost of electricity is the energy times the rate. So if I generate 4,760 kilowatt hours over a year and multiply that times 15 cents per kilowatt hour, dollars per kilowatt hour, then that cancels out, and you get about $720. It doesn't seem like much considering that it did cost me $15,000 to install these panels, so it would take 20 years at that rate to pay for themselves, but I'm going to have them for a long time, I think. You can also maybe compute this one. What about if you're going to dry your clothes, how much does it cost? So again, you could do the cost here is the energy times the rate. Good to be able to compute this. 5,000 watts, and you run your clothes for 1 hour. So E is equal to the power times the time. So it's 5,000, or 5 kilowatts times 1 hour is 5 kWh. So you can usually figure out how much power any of your appliances is using by looking at the back. There's a sticker usually on it. And so you'd get energy is 5 kilowatt hours. And again, multiply times 15 cents. So costs about 75 cents. Okay. So the textbook sticks pretty close to joules for energy units, which is the SI unit, which is good. There are two conflicting definitions of the word calorie, and they're off by a factor of 1,000, and people use them both, and it's very confusing. It's one of the reasons that it's just a pretty stupid unit to use. But historically, a calorie was defined by physicists and chemists to be 4.184 joules, but in reality, nobody really used that. It turns out to be kind of a small unit. So that's called the small calorie, and then there's something called the large calorie, which is 1,000 of those, 4,184 joules, which is also called a calorie. Sometimes, I guess, I remember when I was a student, people would use a lowercase c to mean that's for calorie, or an uppercase c for kilocalorie. But these days, a lot of people use kcal to mean this larger calorie, which is also kind of confusing because what's a kilocalorie? I don't know. But anyway, the textbook says kcal, and what they mean is these large calories. Running apparently, according to the textbook, consumes 740 watts. So how much time would you have to spend running in order to have to burn off the energy in one muffin? Well, again, we're going to use power is equal to E divided by delta T. So T is going to be the energy divided by the power. So actually we need to convert this energy to joules. So we'd get E is equal to 400 of, well, I'll call them kcals, times 4,184 joules per kcal. And you get it's actually quite a lot, 1.67 times 10 to the 6 joules, I think. It's over a million joules. So, and you just plug that in, 1.67 times 10 to the 6. It's really incredible how much energy is in a muffin. And I got 2,300. Does anyone know the units of that? So a watt is a joule per second, right? So I think the seconds comes up here. 38 minutes. So it's about 7 muffins for a marathon, I think. It's called the greenhouse effect. It's good to know about. That's actually a picture from that day when I was shuffling along. There's this thing called infrared radiation, which is anytime anything is warm or even room temperature, it radiates infrared. And there's an energy balance that has to happen on a planet that's orbiting close to a main sequence star, like the sun, which is that there's a lot of energy coming from the star, which is the sun in this case, and going down onto the planet. And that all of that same amount of energy, however many joules, has to get re-radiated back out into space in order to maintain an energy balance. Otherwise, the planet will build up energy and increase its temperature until it's radiating fast enough to make these two things equal. So let's talk a little bit about the greenhouse. So you can actually calculate pretty easily, here's an example, how much energy hits the Earth every second due to the sun and being our particular distance. We're 1.5 times 10 to the 11 meters away from this star, and the star is radiating 3.8 times 10 to the 26 watts. So the way you calculate this in astronomy is that you assume that the sun is isotropically radiating all that energy. So that energy must be spread over a huge, huge sphere whose radius is that distance from the sun. So 4 pi r squared is the surface area of a sphere. You have to imagine that there's this huge sphere. And then the Earth is a sphere also, but 1/2 of it is facing the sun, and the other half is in darkness. So the sunny side of the Earth has, I guess, what I would call a cross-sectional area of a circle of radius r, where r is the radius of the Earth. And so there's 2 areas that are being compared there. You've got the area of the Earth over on this side, pi r squared, and you've got this huge area of the sun. So that power is spread over all that amount. You take the ratio of these 2 areas and multiply. Most of the sun's rays miss Earth and don't even hit us at all. Only this little portion right here in that cross-sectional area hits the Earth. I did a fraction. I did power times pi r squared for the Earth divided by 4 pi times distance squared. And those are big, big numbers. And you end up with 1.4 times 10 to the 17 watts. That's the number of joules per second that impact the Earth mostly in the form of visible light. Now, some of it does reflect. The average albedo of the Earth is 0.3. That's the reflectivity, is that called albedo. That means that the other 70% of that energy, so it's about 10 to the 17 watts, actually gets absorbed by the Earth. If the total thermal energy of the surface of the Earth is going to remain constant, which it kind of has to, then all that energy must be re-radiated out into space. And the power output of the Earth depends on the opacity of the atmosphere to infrared rays, which you can measure. It depends actually a lot on what all the concentrations of infrared absorbing molecules are in the Earth's atmosphere. Idea here is that water vapor is the primary greenhouse gas, but accounts for about 50% of what's absorbing infrared rays that are going out into space. But the global concentrations of water vapor are not affected directly by human activity. And it actually it's quite variable on short time scales. It takes 18 hours, it can change. We don't really control that. What we do control is the next most important greenhouse gas, which is carbon dioxide. So that's about 20% is coming from carbon dioxide, and the other 30% is a list of other gases. Climate change, which is the change in our climate due to human activity, is mostly due to carbon dioxide. And historically, if you look at little bubbles trapped in ice that's very old ice or something, you see that the Earth for a long, long time has had about 290 parts per million of carbon dioxide in the atmosphere. Well, now it's up at 426. Okay, so in every year it steadily rises and rises. So this is a huge problem. And what's kind of scariest about this graph is the problem really is all this carbon that's in the atmosphere. So that's like the problem. The slope of this graph is the first derivative of the problem. And what governments and different policies are trying to do is to reduce the second derivative of this problem, which is that right now the rate that we're adding carbon to the atmosphere is increasing every year. So we're trying to decrease the rate that we're adding carbon. And then maybe if that flattens, we can actually increase or add carbon at a slower rate. And what we really need to do is actually subtract carbon and get it back down to pre-industrial levels. Yeah, so climate scientists have shown that humans are responsible for this global heating that's happening. You can certainly measure the carbon dioxide. Average temperature is now about 1.2 degrees warmer than it was in the late 1800s before Industrial Revolution, and certainly warmer than any time in the last 100,000 years. So this last decade was the warmest on record, and each of the last 4 decades has been warmer than any previous decade since 1850. So there are other consequences to, again, messing with the chemical composition of the Earth's atmosphere. Intense droughts, water scarcity, severe fires, rising sea levels, flooding. Do these sound familiar from the news? Like melting polar ice, catastrophic storms and hurricanes, declining biodiversity. This is all stuff that's actually happening. And there's lots of solutions. Basically, cutting emissions is a good idea. We're going to have to adapt to inevitable climate impacts. We're going to have to finance somehow. Governments are going to have to finance how to change around what we're doing, our activities. But certainly switching energy systems away from fossil fuels and onto renewables like solar or wind will reduce emissions. And we're going to have to cut emissions in half in order to keep warming below 1.5 degrees Celsius. So there will have to be huge declines in the use of coal, oil, and gas.
My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.